Okay, 9.6, the distance from a point to a plane. Okay, so we already looked at the distance between a point and a line, now point and a plane. So this is when we go ahead and extend our equation to ax plus by plus cz plus d. Okay, just take note that we cannot use this as a line. This is the equation of a plane. Okay, so this distance formula actually just extended by basically one variable. So we have the cz in there, and then on the bottom we have that c in there. Okay, and then here's a couple notes. Note the distance between skew lines can be calculated using two different methods. So this is specifically skew lines. Okay, method one, to determine the distance between the given skew lines, two parallel planes are constructed that are the same distance apart as the skew lines. And then what you want to do is determine the distance between the two planes. Now, method two, we can determine the coordinates of points that produce the minimal distance and use the fact that the general vector found by joining two points is perpendicular to the direction vector of each line. Okay, a little bit more complex. Let's start with an easy one. So determine the distance between this point and this plane. So let's just go ahead and sub right in. So we have 8, and we're going to sub in -1 plus, oops, this is going to be -4. We're going to sub in the y, okay, plus 8, and we're going to sub in that -4. Plus 3, okay, all over. We're going to go 8 squared plus -4 squared plus 8 squared. 8 squared plus -4 squared plus 8 squared. Okay, and let's just simplify this. I get -8 minus 8 minus 32 plus 3 on the top. Okay, and on the bottom, I get 64 plus 16 plus 64. Okay, so what is -8 minus 8 minus 32 plus 3? I get -45 on the top. And on the bottom, I get root 144. Okay, note that because we have a scalar, these two bars do not mean, well, they can mean magnitude, but it's kind of like the absolute value. Okay, so we get 45 on the top, 12 on the bottom. When we divide 45 divided by 12, we get 3.75 units. Okay, so therefore, the distance between this point and this plane is 3.75 units. Okay, determine the distance between these two planes. Okay, so if you actually take a look, normal 1 is 2, -1, 2, and normal 2 is 2, -1, 2. So these are the same normals, but then they have different d values. So we know that these two planes are actually parallel. So this is going to look very, very similar to what we did in the previous section, where we need a point on one plane, and then we're going to find the distance between that point and the other plane. Okay, so let's take that second plane right here, and let's find one of like the intercepts. So we can go ahead and like find the z-intercept. Okay, and that means x and y. We can go x equals 0 and y equals 0. So 2, 0, and what I'm doing is very tedious, but that's okay. So you know that 2 times 0 minus 0, so we have 2z equals -16, so z equals -8. Okay, so for that z-intercept, we get 0, 0, -8. And what we can do now is we can go ahead and find the distance between this point and then the other plane. Okay, so the distance formula at the top, we just want to sub in 2 times 0 minus 0 plus 2 times -8 plus 4. And on the bottom, we are going to do a squared plus b squared plus c squared. Okay, 0 I get negative 16 plus 4, absolute value, because that's going to be a scalar. And then on the bottom, I get root 4 plus 1 plus 4. 4 4 is 8, 9. So on the bottom, I get root 9. On the top, I get negative 12. Okay, so absolute value there is 12 over 3. So I get 4 units. Okay, so the distance between these two planes is 4 units. Okay, here's a little bit of an extension onto this question. So I'm just going to put this in purple. Okay, determine the equation of a plane that's equidistant between these two planes. Okay, from these two planes, I should say. So what we're going to start with is we already know the z-intercept of the second plane. So we're going to go ahead and find the z-intercept of the first plane. Okay, so let's sub in again, x equals 0, y equals 0, but for plane number 1. It's 4 equals 0. I get 2z equals negative 4. Z equals negative 2. Okay, so in this case, we get 0, 0, negative 2. So if we were to draw this, what this is going to look like is we're going to have one plane, and we're going to have some other plane down here, okay? And the z-intercepts are going to be negative 2 up here, and down here is going to be negative 8. So if we really think about this, the plane is going to be equidistant between from pi 1 or plane 1 and pi 2 or plane 2 is going to be right in the middle. So we can just go ahead and find the midpoint between negative 2 and negative 8. So all we want to do is add them together and divide them by 2. I get negative 5. Okay, so we know that our plane is going to go through the point 0, 0, negative 5. So let's use that information. I'm going to go ahead and erase everything on the bottom, but we're going to keep in mind that our plane is going to go through 0, 0, negative 5. And then, of course, our plane is also going to be parallel. Okay, so it's going to also have the normal 2, negative 1, 2. So in order to find the equation of the plane that has this normal and this point, all we do is sub it into ax plus by plus cz plus d equals 0. So 2, 0 plus negative 1, 0 plus 2, negative 5 plus d equals 0. Okay, I get negative 10 plus d equals 0. In other words, d equals 10. Okay, so the equation of a plane that's equidistant from plane 1 and plane 2 is going to be 2x minus y plus 2z plus 10 equals 0. Okay, example 3. Determine the distance between this line, L1, and this line, L2. So I'm just going to tell you that these lines are skewed. And if you want to verify that by yourself, you can go ahead. So we know that method 1, what we need to do is we need to create two planes that are parallel and then reduce the question from finding the distance between two skew lines to actually just finding the distance between like two planes, which we've already seen. So if we want to create plane 1, we're going to take the exact same point, negative 2, 1, 0. We're going to take the exact same direction vector, 1, negative 1, 1. And what we're going to do is we're going to use 1, 1, 2 as the second direction vector. Okay, and for plane 2, what we're going to do is we're going to use the point that's on plane 2, which is 0, 1, 0. And then we're going to use the direction vector that it already has, plus t, 1, 1, 2. And then we're going to use the direction vector in the first line. Okay, by making these two direction vectors here, the exact same, we can guarantee that these two planes are parallel. Okay, so what we want to do is we want to take one of the planes, let's just take plane 1, and and we want to find the Cartesian equation of this plane. So what we need to do is we need to take the two direction vectors and we need to cross them in order to find their normal. Okay, so 1, 1, 2, 1, 1, 2. All right, so let's go ahead and cross them. We get -2 minus 1, I get -3. 1 minus 2, I get -1. And 1 minus -1, I get 2. Okay, so that's going to be our normal. So now we're going to have -3x minus 1y plus 2z plus d equals 0. Okay, we need to find our d value. So go ahead and sub in -2, 1, 0. So we get -2, 1, 0. And let's go ahead and solve for d. So 2 times 0 goes away. We get 6 minus 1 plus d equals 0. 6 minus 1 is 5. D equals -5. So the equation of our first plane is -3x minus y plus 2z minus 5 equals 0. Let's multiply that just by -1. 3x plus y minus 2z plus 5 equals 0. So far we have a Cartesian equation for our plane. Now from here, we do the exact same thing as we did in the previous questions, okay? We have a Cartesian equation of one plane. We have a point on the other plane. Let's go ahead and just simply sub these in, okay? Let's switch colors. So distance equals, I'm going to sub them straight in. So 3 times 0 plus, and we're using 0, 1, 0, a point on the other plane, plus 1 minus 2, 0, plus 5. And that's going to all be over 3 squared plus 1 squared plus -2 squared. Okay, so 0 and 0 go away. 1 plus 5 is 6. We can drop the absolute value brackets because it's positive. This value is positive. And we get 9 plus 1 plus 4. So 6 over root 14. And if we were to put this into our calculators, we get 1.6. Okay, so I get 1.6 units. So these two skew lines are 1.6 units away from each other. Okay, just an overview of method 1. We have two skew lines. What we want to do is make two planes, okay, that are parallel to one another. We know that parallel planes are going to have the same direction vectors, okay, so that's easy. And then we're already given the points. Cross them, find the normal, and sub a point back in order to find the full Cartesian equation of one of the planes. It doesn't matter if you use plane 1 or plane 2, you're going to get the same answer. Then with that Cartesian equation and the opposite equation of the plane's point, sub them in and then just solve. That's method 1. Okay, so same question. We're going to determine the distance between these two skew lines, but we're going to use method 2. So we're going to use the fact that when we join 2 points, okay, we want to find the distance between a point and the other line is going to be perpendicular. Okay, so what we want to do is we want to write out L1 in parametric equations first. So -2, 1, 0, and then plus s minus, we can just put s, and then plus s. And let's write out line 2 in the same way. Okay, parametric equations. We can always do a lot more, I feel, with parametric equations. Okay, and just a note, direction vector 1 is 1, -1, 1, and direction vector 2 is 1, 1, 2. Okay, so we're going to have two skew lines. Let's just draw them randomly. And we want to find, of course, the shortest distance between these lines. Okay, so we can represent any point on L1, we can represent by using, let's use U. Okay, so we can represent any point that lies on line 1 as -2 plus s, comma, because that's like the x value, 1 minus s, comma, s. Okay, and let's represent any point t on the second line as t, comma, 1 plus t, comma, 2t. Okay, so if we want to find vector ut, so this is the direction vector of any 2 points that construct one of these skewed lines. Let's say ut. Sorry, let's call this u. T is not here. Okay, u is going to be any point on line 1. Okay, and t is going to be any random point on line 2. And what we're going to do is we're going to find the direction vector of that point on line 1, like between any point on line 1 and any point on line 2. So ut, we're going to do the t minus u. So we're going to go t minus, and this is where the brackets come into place, -2 plus s, comma, 1 plus t minus 1 minus s, comma, 2t minus s. Okay, I'm just going to simplify this a little bit more. T minus s plus 2. I'll go in that order, t, s, and then constant. So we have a t plus s, and then those ones subtract. And then we have 2t minus s. Okay? So that's the general form of any direction vector, between line 1 and line 2. This is where it gets a little bit tricky. So our entire thing is that the shortest distance between these two skew lines is going to be perpendicular. Let's change this color. Let's go green. Okay? It's going to be perpendicular to both skew lines. Okay? That means that ut must, if we dot the direction vector m1 dot ut, it has to equal 0. And if we dot m2 dot ut, that must equal 0 as well. So I'm going to try to fit this over here, just the next part, and then we'll start a new screen. Okay, so I'm going to dot 1, -1, 1, okay, which is m1, and I'm going to dot that with t minus s plus 2, comma, t plus s, comma, 2t minus s. Okay, so it's 1 times this, so we simply get t minus s plus 2 minus 1 times this, so we get -t minus s. Then we're going to just add the last one, 2t plus s. Okay, so let's just collect like terms. I get t minus t, those cancel out, so I just get 2t. So say 0 equals 2t. I get minus s minus s. Oh, and then this is minus s. Okay, minus 3s. And then plus 2. Now we're going to dot the second direction vector. So m2 dot ut, and let's equate that equals to 0. So 1, 1, 2, 1, 1, 2, and we're going to dot that with t minus s plus 2, t plus s, 2t minus s. And I'm just double checking. Okay, so 0 equals t minus s plus 2 plus t plus s. And we're going to double everything in the last one. So we're going to go plus 4t minus 2s. Okay, so I get 1, 2, 6t. And then let's do minus s plus s. Those s's cancel out. I get minus 2s. And then I get plus 2. Okay, we can divide both sides by 2 here. 0 equals, just to simplify, 3t minus s plus 1. Okay, so now we have these two equations in the form with an S and a T in it. Two equations, two unknowns. What do you think we do? Okay, we go ahead and either substitute or eliminate. So we have our T's, our S's, and our constants lined up. However, it's probably gonna, because we don't have the same coefficients, I'm just gonna isolate for S. Okay, bring the S over. I get S equals 3t plus 1. Let's go ahead and sub that into this equation. 0 equals 2t minus 3, 3t plus 1 plus 2, 2t minus 9t minus 3 plus 2, 2t minus 9t, I get negative 7t minus 1. And that equals 0. Okay, bring that over. I get 7t equals negative 1. So t equals negative 1 over 7. Now, I'm going to sub back into this equation. I already did the hard work and isolated for S. Okay, I get negative 3 over 7 plus 1. Well, that's just negative 3 over 7 plus 7 over 7. So I get 4 over 7. Okay, so our S value is 4 over 7. Our T value is negative 1 over 7. So as soon as we have S and T, we just simply sub these two parameters back in to the equations of the two lines. So we can sub as a recall for the x of line 1. Let's call this line 1, negative 2, plus S, which is 4 over 7. So then we get negative 2 plus 4 over 7. I get negative 10 over 7. Okay, for the y value, I get 1 minus S, which I get 1 minus 4 over 7. So I get 3 over 7 for the y value. And then for the z value, I get 0 plus 1s, so I just get 4 over 7. Okay, so the point that I get for line 1 is negative 10 over 7, 3 over 7, 4 over 7. Now we do the exact same thing for line 2. Same color here. Okay, so line 2. I'm just chunking this up. So we can use the board and we can see all the work. X equals, so 0 plus 1t, so it's negative 1 over 7. Then, yeah, y equals 1 plus 1t, 1 plus negative 1 over 7. So 7 over 7 minus 1 over 7, I get 6 over 7. And for z, I get 0 plus 2t. Okay, so for z, I get negative 2 over 7. Okay, so for this one, I get the point negative 1 over 7, 6 over 7, negative 2 over 7. So we have the 2 points that are closest on those two lines. Okay, so take those 2 points and all we want to do is sub them into the distance formula. So we were introduced to the distance formula when we were in grade 10. Okay, the difference in the x's squared plus the difference in the y's squared. And in this case, what we want to do is extend it one more, plus the difference in the z's squared. So we will do negative 1 over 7 minus negative 10 over 7 squared plus 6 over 7 minus 3 over 7 squared plus negative 2 over 7 minus 4 over 7 all squared. Okay, so then what do we get? Negative 1 plus 10, I get 9 over 7 squared plus 3 over 7 squared minus or plus negative 6 over 7 squared. So all of the denominators here are going to be 49. Okay, so I get 81 over 49 plus 9 over 49 plus 36 over 49. And if I add those numerators together, I get 126 over 49. Okay, and if I root that, I get 1.6. So the shortest distance between these two skewed lines is approximately 1.6 units. And again, that's the shortest distance. So that's the distance on the two lines where there's a line between them that's perpendicular to both.